Hello, my name is Hunter Levinson, and this is the Physics 2212 Lab 4 on the magnetic fields of a bar magnet. So for the purpose of this lab, we are going to investigate the magnetic field of a magnetic bar at certain distances from a electromagnetic field. Magnetic fields interact with the phone, aside from the bar magnet and Earth's magnetic field. The bar magnet behaves as a magnetic dipole. The magnet is perfectly aligned with Earth's north-south axis, and the magnetic field strength decreases as distance from the magnet increases. Finally, the location of the magnometer chip within the phone is known. Our results from this are that K is equal to 3.647 times 10 to the negative 7th, N is negative 2.4224, and the magnetic dipole moment of our magnet is 1.8235. So, some fundamental principles for this lab. First is the Biot-Savart law, which basically shows that the magnetic field at any point is equal to a K constant times a cross product of the velocity of a charge times, or crossed with the observation point of that charge. The magnetic field of a dipole is also really important, especially when we are doing equations like this where there are charges that are either on the perpendicular or parallel axis. And this is the general equation for a perpendicular charge. It is just negative 1/2 that of a on-axis charge. And then finally, distance-dependent formula, which just shows that the magnitude of the bar is equal to kr to the n, and this ln function as well, which we're going to use to derive ln and k. So for the experiment procedure, we had to position the phone so that it's aligned perpendicular to the Earth's magnetic field, ensuring that the x component reads 0, and then do the same for the y to determine the precise location of the magnometer chip on the phone, as you can see in the images. We then had to record the distance between the magnometer for both on-axis and off-axis orientations. So for the experiment setup, we needed a bar magnet, a smartphone with a magnetometer sensor, 2 meter sticks, the magnetometer app, and a few pieces of tape as shown below in this image. So for our experiment on axis, this was the data that we got for the values of R20, R70, R120, R170, and R220. The R20 values are the ones that we'll be testing later on. And then we took the ln of both the distance and the magnetic field and graphed it to show the decreasing linear relationship between the two. And this was the m value we got and the b value we got. So we then plugged the m and the v values into our calculations to be able to get that n is equal to negative 2.4224 and that k was 3.647 times 10 to the negative 7th. And importantly, that our mu value was then 1.8235 amps times meters squared. So then we did when we did off axis, as you can see with the images below, especially the one to the right, that our d perpendicular was 0.183 in meters. It was 0.2588, and that the magnetic net field, the absolute value of that, was 8.3765, and that's the value that we're going to be comparing to for our later calculations using coding. So for the computational model, first we have to remember the mu value we got from before, which was 1.8235, and I plugged that in right here. Then I wrote the equation for the dipole magnetic field, using this equation right here that we talked about before. Here's some more code, creating all the orbs axes, making the magnetic field arrows, and then a few more for the perpendicular ones, 4 more that you can't see. And then here are values for the d-perp, the 45 degrees tests as well. And here's the result. We got that the b at 45 degree distance is this, and our d value is 1.66 e to the negative 5th. And as you can see, this shows exactly what we would want it to show. So comparing our results at R20, we got from our code this value, and from our actual, we got that the b was 3 times e to the negative 6th power, which is not terrible, off by about a factor 3, which is pretty good for our testing due to the faulty cameras and stuff and errors that we'll talk about later. And then at the perpendicular, our results were a little bit more off, comparing this absolute value to this absolute value right here is clearly off by a factor of 10 or so, I guess 20, which once again we'll get into the sources of error now. So the main sources of error are that other magnetic fields were likely present. We noticed during our calculations that there were a lot of wires running under the tables and a lot of outlets that were under the table that we were doing our testing on, which obviously would mess with our results. The exact location of the magnometer we likely did not get perfectly right. Also, our meter sticks marks were not very well recognizable, so it's possible that we messed up our calculations by a few millimeters. And of course, like I said, the measurement miscalculations. Now, the what if and why. If we had not orientated our meter stick to compensate for magnetic north, of course, the magnetic field of Earth would be pulling not completely perpendicular to the x component of the magnetic field, and thus it would add to the value and give us skewed results. Finally, if I stuck two magnets parallel together and we recorded the results would obviously be a greater magnitude, as the bar magnet's dipole moment is proportional to the strength and length from pole to pole,